The world of quantum mechanics is strange. It's a place where the laws of physics we observe in our everyday lives break down. In this bizarre realm, energy, momentum, angular momentum, and other quantities are no longer continuous, but are instead restricted to discrete values. These discrete values, called quanta, are the fundamental building blocks of the universe at its smallest scales. Imagine a world where light behaves as both a wave and a particle. Imagine a world where particles can exist in multiple states at once. This is the world of quantum mechanics. Quantum mechanics emerged in the early 20th century as physicists grappled with phenomena that classical physics couldn't explain. Instead of a deterministic, clockwork universe, quantum mechanics revealed a universe that is inherently probabilistic and uncertain. One of the most fundamental concepts in quantum mechanics is wave-particle duality. This principle states that particles, such as electrons and photons, can exhibit both wave-like and particle-like behavior. Imagine a beam of light shining through two slits. If light were purely a wave, we would expect to see an interference pattern on a screen behind the slits. This is indeed what is observed in experiments. However, if we reduce the intensity of the light beam to the point where only one photon is passing through the slits at a time, we still observe an interference pattern over time. Each individual photon acts as a particle, passing through only one slit. However, the photon also acts as a wave, interfering with itself and creating an interference pattern on the screen. The wave-particle duality is not limited to light but extends to all particles, including matter particles like electrons. Another mind-bending concept in quantum mechanics is quantum superposition. This principle states that a quantum system can exist in multiple states simultaneously until it is measured. A classic example of quantum superposition is the thought experiment known as Schrödinger's cat. In this thought experiment, a cat is placed in a sealed box with a device that has a 50% chance of releasing a lethal poison. According to quantum mechanics, the cat is in a superposition of states, both alive and dead, until the box is opened and the cat's state is observed. The act of observation or measurement forces the quantum system to collapse into one of its possible states. Quantum superposition has profound implications for our understanding of reality. It suggests that the act of observation plays a fundamental role in shaping the universe we observe. Perhaps the most bizarre and counterintuitive phenomenon in quantum mechanics is quantum entanglement. This phenomenon occurs when two or more quantum particles become linked together in such a way that they share the same fate, even if they are separated by vast distances. This spooky action at a distance, as Einstein famously called it, has been experimentally verified countless times. Quantum entanglement has profound implications for our understanding of the nature of reality. It also has the potential to revolutionize fields like computing and communication, leading to the development of faster and more secure technologies. Section 5. Quantized energy levels. The quantum staircase. In the macroscopic world, energy seems continuous. However, in the quantum realm, energy is not continuous but comes in discrete packets called quanta. This means that the energy of a quantum system can only take on specific quantized values, much like a staircase where you can only step on specific steps. This quantization of energy is particularly evident in the behavior of atoms. According to classical physics, electrons orbiting the nucleus of an atom should continuously lose energy and spiral into the nucleus, causing the atom to collapse. However, this is not what is observed. Electrons can only exist in specific energy levels, and they can only jump between these levels by absorbing or emitting photons with specific energies. This is why atoms emit and absorb light at specific wavelengths, giving rise to the unique spectral lines that we observe from different elements. Section 6. The Heisenberg uncertainty principle. One of the most profound and unsettling principles of quantum mechanics is the Heisenberg uncertainty principle. This principle states that there are fundamental limits to the precision with which certain pairs of physical properties of a particle, such as position and momentum, can be known simultaneously. The more precisely we know the position of a particle, the less precisely we can know its momentum, and vice versa. This uncertainty is not due to any limitations in our measuring instruments, but is an inherent property of nature. It arises from the wave-particle duality of quantum objects. The Heisenberg uncertainty principle has profound implications for our understanding of the nature of reality. It implies that there is a fundamental limit to what we can know about the universe at the quantum level. Section 7. Quantum tunneling through the impenetrable wall. In the macroscopic world, we are accustomed to the idea that objects cannot pass through solid barriers. However, in the quantum realm, particles can exhibit a bizarre phenomenon known as quantum tunneling. This phenomenon occurs when a particle has a non-zero probability of passing through a potential barrier, even if the particle's energy is less than the potential energy of the barrier. Quantum tunneling is a consequence of the wave-like nature of particles. The wave function of a particle describes the probability of finding the particle at a particular location. Quantum tunneling has profound implications for many physical processes, including nuclear fusion, the operation of transistors, and even the stability of DNA. It is a testament to the strangeness and wonder of the quantum world. Section 8. Quantum fields, the fabric of reality. In classical physics, particles and fields are distinct entities. However, in quantum field theory, particles and fields are two sides of the same coin. Particles are excitations of underlying quantum fields, much like ripples on a pond. Imagine a pond of water. The surface of the pond represents a quantum field. If we drop a pebble into the pond, it creates ripples that spread out from the point of impact. These ripples represent particles. Just as there are different types of ripples on a pond, there are different types of quantum fields, each corresponding to a different type of particle. Quantum field theory has been incredibly successful in explaining the behavior of particles at the most fundamental level. Section 9. Applications of quantum mechanics. Quantum mechanics may seem like a strange and esoteric theory, but it has had a profound impact on our lives. Many of the technologies we rely on today, from smartphones to lasers to medical imaging devices, are based on the principles of quantum mechanics. One of the most well-known applications of quantum mechanics is the transistor, the building block of modern electronics. Transistors are used to amplify and switch electronic signals, and they are found in everything from computers and smartphones to televisions and cars. The operation of transistors relies on the quantum mechanical phenomenon of tunneling. Another important application of quantum mechanics is in lasers. Lasers produce highly coherent beams of light, meaning that the light waves are all in phase with each other. This coherence is achieved by exploiting the quantum mechanical properties of atoms. Section 10. The quest for a unified theory. Despite its incredible success, quantum mechanics is still an incomplete theory. It does not provide a complete description of gravity, one of the four fundamental forces of nature. Einstein's theory of general relativity describes gravity as the curvature of space-time caused by the presence of mass and energy. The quest for a unified theory that can describe all four fundamental forces in a consistent framework is one of the greatest challenges in modern physics. One promising candidate for a unified theory is string theory, which proposes that the fundamental building blocks of nature are not point-like particles, but rather tiny, vibrating strings. String theory naturally incorporates gravity into its framework, and it has the potential to unify all four fundamental forces. However, string theory is still a highly speculative theory, and it has not yet been experimentally verified. Section 11. Conclusion: Quantum mechanics and our understanding of the universe. Quantum mechanics is a mind-bending theory that challenges our classical intuitions about the nature of reality. It reveals a universe that is inherently probabilistic, uncertain, and interconnected. Despite its strangeness, quantum mechanics has been incredibly successful in explaining a wide range of phenomena. It has led to the development of countless technologies that have revolutionized our lives. Many mysteries remain, such as the nature of quantum measurement and the unification of quantum mechanics with general relativity. As we continue to probe the depths of the quantum world, we can expect to uncover even more bizarre and counterintuitive phenomena that will challenge our understanding of the universe and our place in it.